Suppose Alice and Bob share some source of random bits. And we'll also assume that the adversary does not know these random bits. Okay, and this is actually an important case because the quantum case, or the quantum algorithm protocol we're going to present at the end of this discussion is going to look a lot like this. Or rather, it's going to use some of the same ideas. How can Alice and Bob win with, gosh, actually, I think they win with constant number of random bits. Deterministic, so shared randomness. O of 1. Well, the answer in this case is not at all clear. So for those who came in, we started, the problem is Alice and Bob both have strings, and they want to send their strings to some third party in this collective game, and they want the third party to tell whether x is equal 1 equals x2, whether their strings are the same, and they want to send as few bits as possible to the third party. So classically, if they share random bits that the opponent who's trying to trick them doesn't know about, they can do really well. And the reason is they can use error-correcting codes. There exists an error-correcting code. Mapping n bits to 2n bits such that any two code words differ in 2n over 30 bits. So if you have a code word, if you have two code words, then they can overlap in 14/15ths of their bits, but they differ, or 29/30ths of their bits, but they differ in 1/30th of them. So there are error-correcting codes like this, and they're called Justinson codes. And you can actually, write them down explicitly and use them. And actually, there's probably a whole bunch of other kinds of codes which you can write down explicitly that have very similar properties. This is the one that the paper by the paper that by Berman just used as the example, so we'll use this one. Well, there's n bits to 2n bits. Well, obviously, since they're n-bit strings, what we're going to do with this is we're going to have Alice and Bob encode their bit strings. So Alice maps x to the encoded version of x, And Bob maps y to, well, x1 to the encoded version of x1, x2 to the encoded version of x2. And they might overlap in a lot of places, but there's some places they differ in. So, for example, here they differ there, there, and there. And now we come to the great use of the random bits that the randomness that Alice and Bob share that the opponent doesn't know about. I really should call him an opponent because it sounds less scary. Okay, so Alice and Bob randomly choose 60 bits. And they use the same random string to choose it, so they choose the same 60 bits from each of the thing, send them to R. So what bits do they choose? Well, let's say they choose this one, this one, this one, and this one. In that case, the responder would get 1, 1, 1, 1, and here he would get 1, 1, 0, 1. If the 60 bits are the same, answer yes, and if they're not, answer no. Okay, so now we want to know what the probability is that what is probability they fail? If x1 equals x2, the probability is 0 because these are identical things, so no matter what bits you pick from them, they're going to be identical. So with the probability, if they're equal, the probability is 0. If x1 is not equal to x2, well, these two strings differ in at least 1/30th of their bits. So if you choose a random bit, the probability that x equals y is less than 29/30. So here the probability I want to say is greater than 29/30. One minus 29/30 to the 60th, because they're choosing 60 random bits, and each of them has at most a 29/30 probability of being the same. So the chances that all the bits are the same is at most 29/30 to the 60th, and that's approximately 1 minus 1/e squared. Oh, wait, no. The probability that they fail is 29/30 to the 60th, which is 1/e squared. And of course, you can make this probability as small as you want by just sending 90 random bits or 300 random bits or whatever. And it's still a constant amount of communication. So if Alice and Bob randomly choose k bits and send them to R, the probability the algorithm fails is going to be e to the minus k over 30, roughly. Yeah?
So this uses like a logarithmic amount of randomness, though, right?
This uses, how much randomness does it use? Yeah, it uses a logarithmic amount of randomness. Although that's not one of the parameters we'll be counting in our resource. But yeah, because you need to choose some number of random bits, and each random bit counts, log n. Each random bit takes roughly log n to choose. So here, shared randomness was O of 1.